Hello and welcome to this short presentation of Laplace transforms of derivatives. In this presentation we're going to look at the Laplace transform of the first derivative of a function of t and the Laplace expression associated with that, and look at Laplace transform of the second derivative of a function of t and then the Laplace transform associated with that. Looking at an overview of the presentation, we're just going to start by reviewing the definition of the Laplace transform. We're going to derive a Laplace transform for the first order differential equation. We're going to look at some examples of using the first order differential equation Laplace transform. We're going to derive the Laplace transform for the second order differential equation, and then we're going to look at some examples of using the second order differential equations, and I'll leave you with some tutorial questions. Okay, just to recap on the definition of the Laplace transform, which we've seen before. It's the Laplace of the function of t is equal to the integral of e to the minus st times our function of t with respect to t between the limits of 0 and infinity, and we call this equation 1. So what we're going to do now is apply the definition of the Laplace transform to find the first derivative of our function. And I'm using here Newton's notation for derivatives, the f dash, and you'll see the f double dash on the later slides. You might be more familiar with the dy by dx and the d2y by dx squared notation, but I'm sticking with Newton's notation for these notes. So the Laplace transform of the first derivative of our function of t will be the integral of e to the minus st multiplied by our first derivative of t with respect to t between the limits of 0 and infinity. Now, to do this, to undertake this integral, we actually need a process called integration by parts, because what we have in this integral are two functions of t multiplied together, the e to the minus st function, a function of t, and the first derivative of t, of course, is a function of t. So to actually undertake this integral, we need the integration by parts, which may be something, a technique that you may not have come across before. So I'm very briefly going to outline this integration by parts. If you can't follow this particular part of the derivation, don't worry too much, but I will outline it for people that have done this before. When we're dealing with a product and we're integrating it, we start with the terms u times dv. And we're given an expression here for the integration by parts of u times v, take away the integral of v du. This is the formula we use for undertaking integration by parts. Okay, so we have our integral of e to the minus st times the first derivative of t. In this case I will let u equal e to the minus st and dv equals the first derivative of t. So when I'm looking at my integration by parts formula, my integration of u dv on the left hand side is equal to u times v minus the integral of v du. So of that expression, I know what the u value is, I know what the dv value is because I've defined them above, but I don't know what the v value is, and I don't know what the du value is, so I have to find them here. So if we have let u equal to e to the minus st, to find du, I'm going to have to differentiate the u with respect to t, which I'm doing here, and from standard derivative tables, e to the minus st differentiates to minus s e to the minus st, and if I multiply both sides by dt, I end up with this expression of minus s e to the minus st times dt. So I have an expression for du. on looking for the value of v, I start with dv, and to go from the differential to the v term I have to integrate, so dv is equal to the first derivative of t. If I integrate both sides, I'll put a 1 there for clarity, dv is equal to the integral of the first derivative of t with respect to t. When you integrate 1 with respect to v, you get a v, and if you integrate a first derivative, those terms, functions cancel each other out, and we end up with function of t. So now I've got 4 terms, the u, v, the du, and the dv all defined. So if I put them into the integration by parts formula, this is my u and this is my v term in this case, between the limits of 0 and infinity, and I'm taking away from that the v function times the du function, which I have worked out above. That again will be integrated between limits of 0 and infinity. What we notice, if you look at this second line here, and I've highlighted this in blue, this part of the formula, I've just taken the s outside here because s is a constant, and I've changed the positive to a negative because of the 2 double negatives above make the positive. But if you look at this part of the expression, the e to the minus st function of t dt between the limits of 0 and infinity, that integral is actually the definition of a Laplace transform. If you go back to the definition on the previous slide. So actually I can replace, I'll just repeat this line for convenience, I could replace this function here, this integral here, with the Laplace transform of a function of t, because they are the same things. That is the actual definition of a Laplace transform. If I insert my limits over here onto this expression, put in the value of alpha into the e to the minus st function of t, put in the value of infinity, I should say, into the function of e to the minus st function of t, this term will go to 0, because we're basically dividing by a really large number as it tends to infinity. And when I put the 0 into the above expression, the e to the minus st will go to e to the 0, which will be 1, and then we will end up with the t value being 0, so we end up with a function of t at time t is equal to 0, which is what the f open bracket 0 close bracket means. Okay, so what I end up with here, if this is just rewriting the equation again, I end up with this, these terms in the first derivative equation, which I've written down below a bit more clarity here. The Laplace transform of the first derivative of t is now s, the Laplace transform of the function of t, take away the function of t at time t is equal to 0. I've written it underneath just the same expression, but I've written it using Leibniz notation, the dy by dx, and I've changed the f's to y. It's just a different way of denoting the formula there. So what we're going to do now is go through 3 little exercises, just showing the use of the first derivative formula, Laplace transform formula. We're going to prove some Laplace transforms. We've already seen these before, but we're going to use this first derivative equation just to get familiar with it. The essence here is really getting familiar with the terms in the first derivative equation. So this little exercise we're doing, we're going to find Laplace of a constant, and we're going to show that's equal to the constant divided by s. Okay, is the constant here. So the function of t in this case is a constant. In other words, there's no t associated with it here. It's just that value. If we find the first derivative of the function of t, when you differentiate a constant, it disappears from standard tables, so that goes to 0. And if we put the value of t is equal to 0 into the function, we will get k, because it's not dependent on t in this particular case. So taking the Laplace transform of the first derivative of the function of k, I'm going to write my expression using the Laplace transform we've derived. So the first derivative of k is 0 from above, and that's equal to the Laplace transform of k take away the value of the function of t at time t is equal to 0, which we have said is k. So basically what we're going to do now is rearrange the equation. The left hand side I have 0, so I'm going to add the k to both sides to get my k over to this side. That's equal to s Laplace transform of k, and if I divide both sides by s, I get k divided by s is the Laplace transform of k, just turning that equation around. The Laplace transform of k is k upon s. Okay, part B here. We're going to try and prove that the Laplace transform of 2t is equal to 2 upon s squared. We're going to use the first derivative Laplace transform. The function of t in this case is 2 times t, 2t. The first derivative of the function of t will be 2 from standard derivative tables, and if we put the value of 0 into the function of t in this case, we'll get 2 times 0, which of course gives us 0. So we're going to put this into the Laplace transform for the first derivative. So the Laplace transform of the first derivative of 2t, we're going to write in the Laplace transform form here. So on the left hand side, the Laplace transform of the first derivative of 2t, that will be the Laplace transform of 2 in this case, is equal to s times the Laplace transform of the function of t, which is 2t, take away the value of the function of t when t is equal to 0. In this case that is 0. On the left hand side I can write the Laplace of 2 being a constant, as 2 upon s from part A of this question, because in part A we showed that when you find the Laplace of a constant k, it becomes k upon s, so in this case the constant is 2, so it's 2 upon s, and that's equal to s times the Laplace transform of 2t. We're trying to find the Laplace transform of 2t, so in this case we will divide both sides by s, so we end up with 2 upon s squared, proving our original question. Okay, looking at part C here, we're asked to prove the Laplace transform of e to the minus at is equal to s plus a to the power of minus 1. In other words, 1 upon s plus a. We're going to use the first derivative again of the Laplace transform. In this case the function of t is equal to e to the minus at. So when we find the first derivative of the function of t from our standard derivative tables, we will get minus a e to the minus at, and if we put the value of 0 into the function of t, so we get e to the a times 0, in this case that will basically be e to the 0, and anything to the power 0 is 1. We're then going to put these values into the first derivative, Laplace transform. So on the left hand side I get the Laplace of the first derivative of the function of t, which in this case is minus a e to the minus at. On the right hand side I get s times the Laplace transform of the function of t. Take away the value of the function of t when t is equal to 0, which in this case is shown to be 1. All I've done now on the left hand side is taken the minus a outside the Laplace transform, because the minus a is just a constant, it's just factoring up the e to the minus at, and on the right hand side I've kept the terms the same. On the next line I've added 1 to both sides to get the 1 on the left hand side, and I've added the a Laplace transform e to the minus at to both sides to get that on the right hand side. What I've done on the following line is on the right hand side I have factorised on the Laplace transform e to the minus at. That is common to both terms, so I can factorise on that and leave myself in the brackets s plus a. If I now simply rearrange now the equation to find Laplace transform of e to the minus at, that means I divide both sides by the bracket s plus a, and I get 1 over s plus a as a solution, or in the original form s plus a to the minus 1. Okay, that was using the first derivative. Now we're going to look at the second derivative. I'm going to derive that very briefly. Again, a very similar approach here. The difference now is that we're finding a Laplace transform of the second derivative. Note the f double dash, Newton's notation for second derivative. So my integral will be e to the minus st multiplied by the second derivative of the function of t with respect to t between the limits of 0 and infinity. Again, we're going to have to use integration by parts, so same kind of approach as before. I have to define a u term, which in this case will be e to the minus st, and I have to define a dv term, which I will use as the second derivative of t. We've got to go through and find the du term again as before, and we've got to integrate and find the v term as before. I'm not going to labour this in any great way, this solution, just to show you that this time when you put the terms into the integration by parts formula, this part of the expression, this integral here, is actually the Laplace transform of the first order differential equation we proved a few slides previously. So we can actually replace this integral with the Laplace of the first derivative of t. Okay, and that's what's being shown there. If you then follow the imposition of the limits, as we did in the previous derivative for the first order equation, you end up with this expression. Laplace transform of the second derivative of the function of t is equal to s squared Laplace transform of the function of t, take away s times the value of the function of t when t is equal to 0, take away the value of the first order differential equation, first order derivative I should say, when t is equal to 0. So a slightly more complicated expression, although it does incorporate within it the first order solution of the Laplace transform. I've just written it underneath in Leibniz notation, just replacing the f double dash by the d2y by dx squares and replacing the s by the y. It's just different notation. Some textbooks use the d2y by dx squared notation, that's all. Okay, in this example we've got two parts to the problem. We're going to look at part A first of all. We're going to find the Laplace of the sine of t, which is equal to 1 over s squared plus 1. We're going to use the second derivative to show this is true. So in this case the function of t we're given is sine of t. If we differentiate sine of t, we get cos t, so our first derivative is cos t, and if we differentiate the cos t, we get minus sine t, which is our second derivative of the function of t. If we put the value of 0 into the function of t being sine t, so sine of 0 is equal to 0. If we put the value of 0 into the first derivative of the function of t, in this case that's cos t, cos of 0 is 1. So now we're going to put these values into the second derivative of Laplace transform. So on the left hand side we've got the Laplace transform of the minus st, and that's equal to s squared Laplace transform of the function of t, which is sine t. Take away s times the value of the function of t when t is equal to 0, which above we said was 0, and then we take away from that the value of the first differential of t when t is equal to 0, which above we say is 1. Okay, on the left hand side I'm keeping it the same. I could have taken a negative outside the bracket had I wanted to there, but I've left it inside for now. That's equal to s squared Laplace transform of sine t take away 1. I've just removed the s times 0 term, which has disappeared. I'm now rearranging the equation, so 1, I'm adding 1 to both sides, 1 appears on the left hand side, and I'm adding the sine, the Laplace sine t to both sides of the equation to get it over on the right hand side here. The s squared Laplace transform of sine t remains. Now what I'm doing on the next line is I'm factorising the right hand side. Because sine t, Laplace sine t is common to both of the terms there, I can write that as s squared plus 1 multiplied by the common factor, which in this case is Laplace sine of t. To find the solution, Laplace sine of t is equal to 1 divided by the s squared plus 1. I've just divided both sides by s squared plus 1 to prove the Laplace transform. Part B in this case, we're going to prove the Laplace transform of the cos of AT is equal to s over s squared plus AT. Again, going to use the second derivative here to help us solve this problem. So in this case, the function of t is cos AT in this example. If we differentiate cos AT respect to t, we get minus a sine AT from standard derivative tables, and if we differentiate that again, we get minus a squared cos AT for standard tables, which is our second derivative. If we put the value of 0 into the function of t in this case, the function of t is cos AT, we basically get cos of 0, and cos of 0 is 1. If we put the value of 0 into the first derivative of this problem, which is minus a sine AT, we get 0, because everything multiplies by 0 there. Okay, we're now going to put those values into the second derivative Laplace transform. So on the left-hand side, we get Laplace of the second derivative of t, which in this case is minus a squared cos AT, and that's equal to s squared of the Laplace transform of the function of t. The original function is cos AT, and then we take away from that s times the value of the function of t when t is equal to 0, which is 1 in this case, and we take away from that the value of the first differential of t when t is equal to 0, which above we show is 0. So again, just slightly modifying the equation here. On the left-hand side, I've taken a negative outside of the bracket. A negative a squared has come outside because it's a constant, and that's equal to the s squared Laplace transform of cos AT minus s. I've just ignored the last term. Rearranging here, what I've done here is added s to both sides of the equation, and I've added the a squared Laplace transform cos AT to both sides of the equation to get it over on the right hand side. The s squared Laplace of cos AT remains. Okay, what I've done next is factorise the right hand side, so it's s equals to, on the right hand side, I've taken the common factor of Laplace of cos AT outside of a bracket, and inside I've put the terms s squared plus a squared. I actually got to find the Laplace transform of cos AT, so I need to divide both sides of the equation by s squared plus a squared, and that's how I arrive at my final solution. I'm going to leave you with some further problems here on the Laplace transform of derivatives. They basically are the same kind of thing as we've done on the previous slides, to give you a little bit of practice of using the first and the second order Laplace transform equations. Thank you for viewing.